Okay, moving right along. Our next speaker is well known for being the host of the Applied Science YouTube channel, through which he teaches nearly 500,000 subscribers fascinating applications of science and technology. He currently spends his days working at Verily and Google Life Sciences, and the remainder of his time prototyping electromechanical devices, including health sensors and more, for which he has been featured on the Hackaday blog and past Hackaday Superconferences numerous times. Please welcome to the Hackaday Superconference stage, Ben Krasnow.
Thanks very much. I've got a 2-for-1 special talk for you tonight. The first half is going to be talking about putting copper onto plastic substrates to make circuits. And the second half is going to be how to put these electroluminescent displays on plastic. And the total goal here is that you'll be able to have mechanical parts, snap fits and that sort of thing, with electrical circuits and optical displays all in one solid chunk of material. It's the most alien technology that we can currently make in our shop. And the best thing about it is that most of you can do this with the tools you already have access to. The major push of this research is to get this done with standard laser cutters. Just to basically already said this, but yeah, this is exactly what we're going to talk about. There is existing plastic or copper on plastic tech, which I'll cover. The new method, this is actually novel research that Mike alluded to in the opening speech today. Then the luminescent stuff. And then also, I think a lot of you have seen this glove that I'm wearing here. There's a circuit board on here that's driving the electroluminescent, and there's some novel stuff to talk about there too. So just to give an example, or reference point of where this project is, we're kind of at the first prototype stage. So this is the graduated cylinder of development. And you might have just random ideas at the bottom, and as you pour and pour more and more development into it, you raise the level in the cylinder. So currently, we're kind of at the first prototype stage. It works. The thing you're looking at on the right is my prototype unit that shows a working electrical circuit on the plastic substrate. And it's not really ready yet for beta testing, or kind of the first batch. But as you'll see throughout the presentation, if you want to get involved with this, there's plenty of stuff to work on. Let's get a closer look at the circuit. We have 0.5 millimeter pitch trace space. And this is a QFP package here that's running a microprocessor, quartz crystal, some 0402 LEDs. The plastic is actually translucent, so if you look at the red LED, it's flashing on the other side, and you can see it through the substrate. And the way that this method works is that you get copper wherever you hit the plastic substrate with the laser. So if you use the laser to make a through hole, the laser touched it to make that hole, and you get a plated hole. So actually with this method, you get free plated through holes, which is a major benefit. A lot of people asked how I put these things together. It's just standard lead solder with hot air reflow. So there's nothing weird going on. It's not super temperature sensitive. The substrate can maintain hot air reflow temperatures for a short time with no problem. So I should add that there are currently technologies available for making copper on plastic. And in fact, this little gizmo that you're looking at is a trade show sales pitch piece made by a company called Multiple Dimensions. And the cool thing about Supercon is the founder of Multiple Dimensions is actually in the audience right now. Which is also a great reminder why to never be too negative, especially when you're putting slides together that might mention people or companies. Very important. And as you can see, this is a cool little demo unit. It's gold-plated, and it's two-sided. It doesn't have any through holes, but apparently the current tech can support through holes, but I have not seen it myself. You may wonder why you even want this in the first place, right? I mean, okay, it's cool, so that's a given, but realistically, the benefit here is that you can put mechanical elements into your circuit, so it's really the same chunk of material. So currently, whenever you make a low-cost consumer electronic device, you've got like basically a plastic box that might be shaped pretty cool, but it's a plastic box. And then you got to mount a circuit board into it. And then you have little connectors that connect the circuit board up to all the sensors and buttons and everything that goes to the outside of the box. In a future vision, maybe the box is the circuit, right? Like that's the joke. Like it is the same piece of material. And you'll see as we go through the talk why that makes sense. You probably have one of these plastic or copper on plastic devices in your pocket right now. They're actually really popular for 3D antenna designs in cell phones. And the reason that they're so good is because the antenna designer can use 3D space to make an antenna, but the space is filled with hard plastic, so it's mechanically very stable, as opposed to like a flex circuit that doesn't really have any mechanical stability of its own. If you use one of these pieces of plastic covered with circuitry, you can put your body weight on it and it's still mechanically okay. So it has these really great properties of being able to route electrical signals at the same time being a mechanically useful piece of your product. Currently, they're kind of expensive, so under the future reasons column, I put down cost savings once widely adopted as a benefit. So currently, the only way that you would get one of these is in a cell phone. It's like a mass-produced piece of equipment. But in the future, when the costs come down, this would make sense for a lot more pieces of technology. And it looks really cool too. These are just, actually this is a, I think a Nexus cell phone antenna, and the picture on the right is a fanciful version of the future there. Here's a couple more examples of how you would actually use this technology in real world products. On the left, there's a smoke detector. And in the upper version, that's kind of how it's built now, where you have one green circuit board, some flying leads, just cheap pieces of wire connecting the different components to the circuit board and the battery. And the bottom version shows what this could look like in the future with this plastic or copper on plastic technology. And you eliminate all of the assembly work of putting all these separate wires onto the board. So even though the actual part may cost a little bit more, you end up saving quite a bit of money in the assembly. And you'll have to do the numbers to figure out if it makes sense for your specific product. But besides looking cool, if you save a lot of money on assembly, that makes the bean counters happy too. So everyone wins. It looks cool and it might be cheaper to make. On the right, you see the motorcycle hand grip. The benefit here is that you can have buttons coming off at any which angle you want to make it the most ergonomic thing possible. And you could say, well, I could do that with a flex, and that's true. But if you mount those buttons to a flex, now you still have to have the mechanical issue of getting the button permanently fixed to the hand grip. The benefit with this is that you have the circuitry there, and if you solder your button down or use a mechanical fixture to go into the MID, it's mechanically locked in and you get a much better connection to it. Also, I'll admit that I don't know the future, so when I say that the future involves copper on plastic circuits that sort of take over this whole like hybrid mechanical circuit board thing, I'm not really sure about that. But what I am sure about is that circuits in the future won't look like what they do today. And I put this slide in here just to remind all of us to think about what circuits will look like in 5 or 10 years. I put a little sort of progression from old to modern here just to sort of remind us of how things have changed. On the left, there's a Geiger counter from the 1940s. And then there's like a circuit board from the 90s in the middle, and then a PDA from the 2000s. And then next could be copper on plastic. Let's talk about how they make these existing MIDs. By far the most common process is called this laser direct structuring. And so the way that this is made is you injection mold your plastic part, standard injection mold process, but you add some special powder to the injection mold material and you mix it up so that the powder is nice and distributed. And this special powder is a catalyst. The catalyst will cause copper to be deposited there in the next step, but just keep in mind it's just a special dry powder. And the mix ratio is typically about 10% by mass. So the plastic will look gray or black always because this powder is gray or black. And when you mix it into the plastic, that is what color it will be. A couple of problems with this technique. One is that there's basically one company that does this. And so there isn't a whole lot of competition or sourcing to do it. So it's difficult to get started. Plated through holes are difficult because of this method, which we'll talk about. And prototyping is slow and expensive because of the injection molding. And there's a couple ways that we can address this, but really the whole point of this research and the talk that I'm doing is to show you a way that you can prototype this stuff on your own without the injection molding equipment and without the YAG laser, which is what's currently used for this LDS process. And currently, right now in the current economic condition, you would not use this to make a smoke detector. It would be way too expensive. So we're definitely thinking of future applications. And the point of worrying about prototyping now is that it's all of us that are going to be coming up with these cool prototype ideas that are going to be taken to production later on. So having the toolkit now for prototyping really makes a big difference. So you can get a sense of scale from the size of the machine that you need to do this. This machine in the middle here is a YAG laser, and what it does is ablates away the surface of that injection molded part that has the special catalyst powder in there. And when the laser hits the surface, it basically blows off the top layer of plastic, exposing little bits of catalyst particles to the surface. And this is great because where the catalyst is exposed is where we're going to get copper deposited onto the object. So I've got a blue arrow here on the bottom just showing kind of what stage we are in the process. And to their credit, they knew that prototyping was going to be a big problem here because you need to invest in injection mold tooling, which is expensive and slow. So this company came up with a spray paint, which I thought was a pretty novel idea. I haven't tried it myself and don't know much about it, but you can 3D print a part and spray paint it, and now it has this coating of catalyst embedded in the spray paint on the surface. So now you're kind of back to where you were with an injection molded part. Now you can hit it with the laser and expose that catalyst. You still need the expensive YAG laser, and in one of their sales brochures they are touting this machine that was on wheels and could be rolled through a lab doorway as like a pretty big benefit over the one that you can't wheel through a lab doorway. It's very expensive too. So after you've laser ablated your part where you want copper and exposed this powdered catalyst, you dip it in a magic coating solution, electroless copper, and you wait about 30 minutes or an hour and take it out, and you'll have a copper trace there. Pretty cool. This may or may not involve electrical plating. So the big trick with electroless copper is that the solution will deposit copper wherever you have catalyst exposed. It doesn't matter if you've connected it to a battery to run electrical current through there. That's a different process that uses electricity to do metal plating. So I decided to try it, and I figured the easiest way to get started was just to replace the expensive parts with cheap parts. So I got rid of the injection molding machine and used an SLA 3D printer. And the reason that I like this printer for this project in particular is because the surface is very smooth. So if you want to do an electrical trace, you really can't have like the ridges from an FDM printer because following the copper trace over those ridges is a big problem. So just to make life easy to start out, I'm using an SLA printer. And I'm going to replace the YAG laser with this eBay 60 watt import laser. It doesn't work. I tried it, and it makes a little bit of smoke, and you'll see in the next slide I got something cool out of it anyway. But I tried a few different things, and my conclusion was that you really do need the YAG laser because it has a really high pulse power. So the difference between a CO2 laser and a YAG laser is that the CO2 is basically continuous wave, so it's like 60 watts all the time. And a YAG laser is like thousands and thousands of watts for a really short burst, and then it moves over and does the burst again. So you get like this trail of really high intensity laser bursts. And you really want that high peak power because it vaporizes the plastic in one big swoop and leaves the catalyst there. Whereas if you just hit it with a CO2 laser, it just kind of melts everything and just makes a big mess of it. But we got something cool out of it. If you mix copper oxide, which is another potential catalyst powder, into a plastic matrix, this is just 2-part epoxy, and defocus the laser so that you have a really broad beam that's actually not very hot, you get this really cool effect where you can make a copper trace on the surface without any prep or further processing. And I've got the meter over there showing that it's only 10 ohms across that centimeter of the track. That's pretty cool, and so I actually kept working at this method for a while. The biggest problem is that the surface here is pretty lousy. I mean, it's very rough, and the trace of copper is really not adhered very well to the plastic at all. It looks good though. So I put that aside and started to work on the chemistry. So regardless of how the catalyst thing was going to work out, I needed to have a way to coat copper onto this project electrolessly. And so here's the complete process. And in all of my hours of research, I've never come across a slide that actually has all of the recipes and the entire process all summarized in one place. So this is actually like a critical mass of electroless copper plating. And yeah, take a picture of it or save a slide deck or something, because this is probably 10 or 20 different sources all put together and tested for you, which is pretty nice if you want to get into electroless copper. All the chemicals are available on Amazon and eBay. And if you don't want to mix them yourself, you don't have to. There's this place called Caswell Plating that will sell you the whole kit. It's very expensive. They want about $150 for the kit. And if you took the $150 to Amazon, you could have enough chemicals to plate an entire car in electroless copper, probably. It's actually very cheap chemicals. And then the last concern is that it's dangerous, so the chemicals are bad. And you know, I'm not going to lie, they aren't great, but about half the chemicals that are in the electroless bath are sold literally for you to dump down your drain. So the sodium hydroxide is drain opener, which you take home and dump down your drain. The copper sulfate is a root killer, so you also dump that down your drain to kill roots. And the washing soda you can use to wash clothes if you want it. Again, just dump it down your drain. I'm not saying that's good, but the way the laws are currently written, it's totally fine to dump all these down the drain. Yeah. I almost skipped the catalyst bath. So the electroless bath has all those chemicals that I just mentioned. This magic catalyst bath, if we don't distribute this catalyst powder into a plastic before injection molding it, we still need a way to get the catalyst onto the surface. And so that is actually a mixture of palladium chloride and stannous chloride. And what happens when you mix these two things together is it makes a colloid of palladium particles. And a good way to think about how this is going to work is imagining dipping your hand in water and then dipping it in dry sand at the beach. When you take your hand up, you'll have this really fine coating of sand on your hand. And that's basically analogous to what's happening when we put a part into this colloidal palladium catalyst. We dip it in there and the palladium particles are attracted to the surface, and when we take it out, the whole thing is saturated with catalyst and ready for plating. And here's the result. If you print, this is a 3D printed cube about 20 millimeters on a side, and it came out of the Formlabs printer. I dipped it in the cleaner bath, the Alkanox there, and then dipped it into the catalyst, let the sand particles of palladium stick on the surface, and then dipped it into the electroless copper bath, and you take it out and you have a perfectly fully plated thing of copper. So what you could do is now take this and put it into the laser cutter and just blow away the copper where you don't want it. That actually works just fine. The only problem with that is it's sort of like a negative process, and that won't really work very well because you can't get every nook and cranny. What you really want is a positive acting process so that you only get copper where you hit it with the laser. That's really a pretty big deal. So the subject of all of my research that I put into this was to figure out how to get a positive acting laser activated copper deposition on these 3D printed parts. We're going to talk a little bit about the surface chemistry because that's how this whole thing works. So we're going to assume that wherever we have catalyst stuck to the surface, we're going to get copper. So the whole question comes down to how do you control whether the catalyst actually sticks to the surface of this thing or not? And I like my sand analogy because you basically want to do something to your hand when you dip it into the sand that will cause the sand to only stick where you want copper to be. And that's basically what's going on here. I don't think it's worth going into the super details here, but the tin and the palladium work together to create this colloid that when you dip in there, you get the stuff stuck to the surface. The electroless copper process is pretty cool. I want to spend a bit more time on this. Think of it like a opened carbonated beverage. So you mix the whole thing up, and now you're on the clock. Like it's basically like opening up a soda and just leaving it on the counter. It's a unstable bath of stuff, and it'll work for a few hours or a few days, depending how aggressively you mix it, and then it will expire. That it has like a time limit. And so the nice thing about buying your own chemicals on Amazon is that you can mix up a new batch every day, whereas you'd be spending a lot of money with Caswell if you bought it from them. The way this thing works is that the copper is in solution in this electroless plating bath, and there's formaldehyde in here that's going to try to reduce the copper and cause it to just drop out of solution. And if we can control where that happens, then we get copper deposited on the surface, which is where we want it. The other trick is that the pH of this bath will regulate how aggressive the thing is. So basically, how quickly the soda is going to go flat. It's actually a very convenient way to adjust this. So you can dump in a whole bunch of sodium hydroxide and actually get all the copper to fall out of solution all at once, all by itself. The bath has crashed, as they say. You can also have a pH that's too low, and the bath won't plate at all. It's sort of like a way of pausing it. In fact, if you're good at controlling the pH, what you can do is purposefully lower the pH at the end of the day, and then come back the next day and raise the pH, and the thing will be back to being active again. So here's the research. Here's my final solution that ended up working really well. We know that if you don't clean your part very well, the catalyst will not stick to the surface. Seems pretty reasonable. And so if you test this process out before doing anything special to the surface, we'll find, and you put it in the laser and then do the whole plating with catalyst and then in the electroless copper, you'll find that it's actually working exactly oppositely the way we want. What we really want is the catalyst to adhere only in areas that have been hit with the laser, but we have two problems. It sticks to the place that we haven't lasered, and it doesn't stick to the place that we have lasered, and so it's unfortunately completely inverse. So the solution to the first problem is to purposefully make the surface dirty so that it won't stick. And I found that the best thing to use is this TriFlow superior lubricant, which is actually a superior lubricant. I use this instead of WD-40 now in general. Actually, it's pretty good stuff. It's also cheap and on Amazon, and it might even be in your shop now, which are other benefits. The other secret ingredient is this stuff called Wet and Forget, which is it's a moss killer. It sounds completely random, I know. A funny thing about moss is that it doesn't, Roundup won't kill it. So Roundup kills most leafy vegetation, but it does not kill moss or algae. So they've come up with this other product called Wet and Forget that disrupts the cell membranes in moss and kills moss. It's for like driveways if you don't want your driveway slippery. The cool thing about this chemical is that it is a surfactant, a surface active agent. And it will allow things to stick to the surface because it basically goes between the surface and the thing that we want to stick to the surface. I'm going to skip that. This involved quite a lot of trial and error. This was about 80 hours of R&D, and if you saw Mike's talk, he actually used this same slide in his talk, so this must be a good one, that shows my trials and tribulations to get all of this done. It's a little bit of a binary search, like it's kind of like you try something, did it work or not, then you base something on that, and you end up with this tree of progress with lots and lots of dead ends, and then you have to back up and make a new branch. But it's sort of like an informed search, where I kind of knew what I wanted to do with surface treatments and surfactants, but there was still quite a lot of trial and error. I also wanted to, this slide reminds me, think back to the last time you were having a difficult problem, like you've been working on a microcontroller for 8 hours, it's 2 in the morning, it's not working the way the data sheet says. In that sort of system, it's very frustrating, but you have to remember that that system was created by another human to be usable. This is like completely off in the weeds. There's literally no manual. There's no one's writing about this. It's a completely novel process of using surfactants to control adhesion based with a CO2 laser. And so it's a whole different mode of operating. So the final process, print the object, clean it with Alkanox, dip it in TriFlow, put it in the laser, dip it in DBAC, Wet and Forget, dip it in the activator, dip it in the plating solution, and then clean it off, and you have the circuit board. It's a few steps, but it's not at all difficult. You'll notice that all the examples that I've been showing are flat, so it's not exactly 3D printed, is it? The trouble is that the real difficulty in this project was figuring out the chemistry. I think the 5-axis stuff to actually do 5-axis circuit deposition is kind of like a secondary thing. You can also get a super smooth surface if you start with a super smooth substrate. This process works on acrylic, does not work on ABS, does not work on PLA. We're going to shift gears here and go into the electroluminescent deposition stuff. I know we're running a little over, but I'm going to take another 5 minutes at least. I think it's worth it, trust me. This is really cool stuff. And so I also went fast, because if you're interested in the copper deposition stuff, I have a whole YouTube video on it, and it's more or less in the same state as at the end of the YouTube video. But I have learned that there's this company that sells paint that you can spray onto any surface you want, and then deposit electrodes onto it, also sprayed on. And when you apply power, you get this electroluminescent surface. It's a very well-developed product. It's made for the car industry, so that you can have like pinstripes and like entire fuel tanks on motorcycles light up and stuff like that. You can even paint over it so that you get like an illuminated picture effect in the masking that you see here, the lambda sign. Here's a stack up. So these guys don't know anything about copper deposition, but when you put this together with the tech that I've been describing, you can actually lay out an entire display in the copper defined by the laser. Then when you put this electroluminescent paint over it, you can have any display you want on a curved surface, on plastic, with mechanical features all integrated. So that's like the dream. Like, that's what we're going for here. Downside is the kit's kind of expensive. It's $450. Okay, that's high, but it is pretty cool, and it does work very well, and the documentation is pretty good, so they did a good job there. And it also looks like a lot of layers, but you don't have to do most of those. You really just need the backplane, the dielectric, the phosphor, and this conductive top coat. You can do pretty cool stuff with it. I'm not going to steal all their images, but if you like this, go to lumalore.com and you can see some really cool examples, especially cosplay. Here's me depositing the electrodes. Full disclosure, I don't have this working with the laser-defined electroless copper deposition process, just because the surface smoothness is a big problem. And so testing this out on a smooth piece of acrylic makes things much easier. Spraying it out looks really cool. I've got an ultraviolet light off camera there, and when you're spraying the phosphor, everything glows, which looks great. I'm going to skip really fast through the driver stuff. This is all on GitHub. If you search for EL driver multi, it's on the next slide. You can get all the details. KiCad, Arduino, processing.org, everything about it is open source, and it's all up there. I also found these really cool tiny transformers. That's the grain of rice next to it. And it's a 10-to-1 transformer that's meant for charging up capacitors for xenon strobes in cameras. I've repurposed it here just to generate a 250 volt supply. I'm going to skip this. This driver chip is pretty cool. It takes the 200 or 300 volts from those transformers that are running in flyback mode, and I have 64 channels that I can address at 300 volts coming out of there with a pretty quick refresh. So what this chip is basically an 8-byte shift register with a 300 volt high voltage output and a latch. So with all these channels available, I thought I have to do a matrix. But before I invest the time to build the whole matrix, I'm going to do a 4x4. And I thought that looked pretty good. So then I went for a 32x32. And this one, this looked pretty good too. This is very encouraging. And so my method for doing this was to use a drop of UV glue to hold the wire down, and got all the wires down, and then I used some conductive epoxy to connect it up. And then I thought, well, it's looking pretty smooth. I'm running at about 30 frames a second. I think the next step is like full video. So I put a diffuser over it. This one sounds better with sound. I think my volume's up. I'm actually glad that it was.
We're no strangers to love.
That's great.
You know the rules, and so do I.
So that's all I got for you. And I will see you next year.